Welcome to the fifth and final installment of this review of 3D vectors for IBHL math. Again, these problems are taken from the Cambridge textbook, so follow along if you got it. I can't remember what section this comes from, A, B, or C from the chapter, I believe, 13. Anyway, here we have points that are located by two position vectors, and basically when we the second position vector is basically predicated or based off of the parameter t. The first vector is fixed, and what we're going to do is we're going to add these two vectors together, and depending on the value of t, it's going to make it so that points p and q are going to have certain distances apart. What we're trying to do is get the smallest distance possible between points p and q, given these two vectors. And if you notice the way that the ooh, hey, that was fast. If you notice the way that the vector q is given, it's actually a vector 2, 1, 1, and then it's starting off in a direction of 1, negative 1, 1, times a scalar multiple of t. So in other words, the vector q is actually given to us in a form very similar to what we had in the previous exercise. So once again, the authors are sort of teasing you into understanding what a vector equation of a line is, and to get a better understanding of how q works, q is again dependent on time, and so this vector q is going to be in a different place. It's going to be in a different location as I continue to change t. And it turns out that you can find a line that would fall on, and that stuff again we're going to study a little bit later. But here we can find vector pq, and we would like to minimize the distance pq, so first we need to find a way to establish the distance pq. Remembering from our skills training that if we subtract vector p from vector q, that we would have the vector pq, and so there's the vector q, subtract the vector p, and it gives us a new vector for pq, and then all we have to do is use our magnitude formula, which is based off the Pythagorean theorem on steroids, and we get this quadratic under a radical. Now, we've studied calculus at this point, but at this point in the textbook, we haven't had calculus, but that's okay. We do understand that we could, of course, use derivative to find the minimum value of this now function for the length of pq. However, it turns out that underneath the radical is a parabola, and the assumption is since it's a parabola opening up, it will have a minimum, and that minimum will occur at its vertex. So just to show this work, I'm just going to complete the square, which is one way of finding the vertex, and I find 4 1/3 is the lowest value of that parabola. So we just have to find out at what time does that happen. It happens when t equals 1/3. So if t is equal to 1/3, that's going to give me the smallest distance possible for the line segment PQ, and that smallest distance is going to be 4 1/3, square root, the square root of 4 1/3. So just to verify, I did want to go in and kind of see what the vector is going to look like, and also wanted to make sure that the minimum was where I said it would be, and so all of this stuff does indeed check out. I even used GeoGebra to program in that shortest distance as well, and it happens when the parameter, which I was able to create a slider here, can't see it right now, probably because it's not. Anyway, I checked it out with technology. I encourage you to do the same. Not even if you know the answers right from the back of the book, it's worthwhile to make sure that technology can back up what you're doing, and that you know how to use the technology to back up what you're thinking. So I went through this really quickly, but I hope you find this work to be helpful for you. Once again, it's a good idea to use three-dimensional renderings as whenever possible, and it's a good idea to spend some time developing some understanding before you just dive right in and apply the algorithms. That's what I was trying to accomplish with this video series, and give me some feedback if you don't think I did accomplish that end. Anyway, thanks for watching. Have yourselves a great day.